Perhaps one day our descendants will awaken beneath another sun, not as ghosts of a frozen age, but as dreamers who carried humanity's dawn into the next. Sleep has always been one of humanity's great mysteries, a daily surrender to stillness that somehow restores us, a voyage through dreams that resets our minds for the waking world. One wonders why evolution permitted such a protracted, vulnerable period every day, and I can imagine seeking technological or genetic workarounds to cut down on sleep without other losses. And yet, in the far future, it may become the key to crossing the gulf between the stars. If we cannot outrun time, perhaps we can sleep through it. Space, for all its wonders, is not friendly to the impatient. Even our fastest robotic probe crawls along at a fraction of a percent of light speed. For a human crew, that means months or even years just to reach Mars, decades to reach the outer planets, and centuries to reach even the nearest stars. You can build bigger engines, burn hotter fuel, or try to stretch physics to its limits, but the numbers are merciless. When you start measuring journeys and lifetimes, you begin to ask whether the travelers themselves should wait out the voyage in another way entirely. That's where the dream of the Cryogenic Ark begins, a ship that doesn't so much travel through space as it drifts through time, carrying its crew frozen in stillness until they awaken beneath another sun. The idea has been around for centuries in fiction and philosophy alike. H.G. Wells imagined long sleeps in the future, and modern science fiction built whole genres on sleeper ships, vessels where time passes for everyone except those who dare to dream the long dream, and voyage to strange new worlds. Of course, as I pointed out in our original episode on sleeper ships, at the moment you are not asleep, you are dead, a frozen corpuscle who we have no way yet to revive, and most of the technologies that would permit thawing and regeneration can also probably extend life beyond its natural duration. It is probably easier to maintain healthy cells than to repair frozen ones. Our earlier look at sleeper ships almost a decade back explored many of these ideas, the psychology of waking in an alien era, the ethics of freezing a crew, the technology that might sustain them. But that episode was recorded before the recent leaps in cryobiology, suspended animation research, and quantum-level preservation methods. Today, we revisit the concept with sharper tools, to ask not merely if we could sleep through the ages, but how long we could last, and what new dangers emerge when even time itself seems conquered. Because space travel isn't just about reaching your destination, it's about surviving the wait. The need for cryogenic arks. If you are sending a ship to another star, there are only three ways to beat the tyranny of distance: go faster, live longer, or stop the clock. Relativity locks the first behind a wall of infinite energy. I do not expect us to ever find a way to travel faster than light. Biology might grant the second, a longer life, through genetic engineering or medical immortality, and I am optimistic about this option, but the third, freezing time for the traveler, remains tantalizingly simple in concept and monstrously difficult in practice. Cryogenic arks solve a number of otherwise unsolvable problems. The first is energy. A living crew must eat, breathe, stay warm, and maintain artificial gravity and light for themselves and their crops. Even on a modestly long voyage, those systems consume immense power that must be generated and maintained for centuries. Freezing your passengers reduces your ship from a small city to a well-insulated warehouse. It can cruise silently and cool through the dark, shedding little heat and attracting little attention. There is a caveat. It is worth noting that for any speed above 1% of light speed, the energies needed to get up and down from those velocities tend to dwarf even multi-century life support needs. It is still beyond huge, though. The second problem is entropy. Anything mechanical decays over time. Metal fatigues, plastics outgas, lubricants dry up, microcircuits suffer from cosmic radiation, and everything leaks. The colder your ship runs, the slower all those processes occur. In that sense, freezing the crew and cargo is just one part of freezing the ship itself. A cryogenic ark becomes a time capsule as much as a transport, a vault of matter and memory waiting to wake. The third challenge is human continuity. A generation ship can take your descendants to the stars, but they are not the people who left. Their language, culture, and priorities will evolve in transit, and by arrival, they may not even want the same mission. Cryogenics lets you preserve not only the genome but the civilization that launched the voyage. The same crew, the same ideals, the same mission parameters, arriving as they departed, even if the universe has shifted them around. And finally, there's the human factor, psychology. Long isolation in the void may be worse than death for morale. Boredom, despair, and cultural collapse could destroy a mission faster than a mechanical failure. Freezing the crew eliminates the risk entirely. They sleep through the centuries without fear, boredom, or rebellion. The ship becomes an ark in the truest sense, a vessel that carries life safely through time's flood. Of course, all this assumes you can safely put a human being on ice, stop every chemical process in their body without destroying the delicate machinery of life. It sounds simple enough. Just cool someone until nothing moves. But at the atomic scale, nothing is never still. Molecules jiggle, bonds stretch, water crystallizes into knives. That's why the next section of our journey will take us into the science of stopping time inside the cell, from antifreeze and genetic engineering to the quantum tricks that might let us turn death itself into dormancy. From freezing flesh to preserving life. If you ever left a soda can in the freezer, you already know the first problem with cryonics. Ice expands. The moment water freezes, it forms sharp-edged crystals that tear cells apart from the inside out. A human body is mostly water, which means that freezing someone solid isn't so much putting them on pause as turning them into biological shrapnel. The real art of cryonics, then, is not freezing people, it's freezing without letting ice form. Incidentally, the terms cryonics, and cryogenics all get used a lot in these conversations. Cryonics is specifically freezing dead people, while cryogenics is the study of phenomena that occur at extremely low temperatures. Cryo is from Greek for frost. We could have called the episode Cryogenic Arks, but that wouldn't be right, because we're assuming the whole ship is cold and often ultra cold, and at most has a warm habitation bubble for a maintenance crew. We need to freeze more life forms than just people, for an Ark ship to bring Earth life to a new world, and most of the challenges are the same for freezing a person as an elephant, though some life forms are freezer ready. But more to the point, we have all sorts of other non-organic cargo that needs to be designed for cold temperatures. Freezing critters without their cells exploding is our biggest challenge, though. Modern cryobiology takes that challenge seriously. We've already learned to freeze embryos, skin grafts, and even organs for limited periods using compounds called cryoprotectants, anti-freeze chemicals that replace water inside cells and keep them from crystallizing. The trick is to cool tissue fast enough to halt chemistry, but slow enough to avoid forming destructive ice. If done perfectly, you get a glassy solid known as a vitrified state, where molecules are locked in place like amber. Nothing moves, nothing decays. And yet, with the right care, it can all be restarted later. Still, what we can do now is a far cry from freezing a person. A mouse brain or a small organ is one thing, a human body is another. At present, the processes cause damage at the molecular level. Cell membranes rupture, proteins denature, and even DNA can shear under thermal stress. We can't revive a whole mammal from deep freeze yet, but research in vitrification and nanoscopic tissue repair is advancing rapidly, driven in part by organ banking and trauma medicine. Research then is not solely dependent on those wanting to freeze humans like Buck Rogers or Fry. The tools being developed to repair damage in a frozen liver might one day repair an entire frozen human being. Nature, of course, beat us to this idea. The wood frog can survive being frozen solid for months, its heart stopped and blood replaced with sugars that act as natural antifreeze. Antarctic fish make proteins to prevent ice from forming at all. Some insects and microbes endure desiccation so complete they become powder until water returns, a process known as anhydrobiosis. The infamous tardigrade, or water bear, can survive decades in that state, shrugging off radiation, vacuum, and freezing alike. Evolution, it seems, already solved the problem of suspended animation millions of years ago. We simply need to reverse engineer it. Of course, these critters are all small, and that helps a lot. Temperature changes are slowed by size. Sleeper ships don't necessarily need to involve freezing people either. Ignoring sci-fi options like freezing time, we can't just cool people. NASA and DARPA have both studied short-term hibernation as a means to reduce life support requirements for long-duration space missions. Lower body temperatures, reduced oxygen demand, and slower cellular repair all translate into fewer supplies and less wear on ship systems. It's not quite freezing the crew, but it's a step toward it, a sort of controlled torpor, like bears use for winter. In space, the cold vacuum outside makes such states easier to maintain, if you can stop the formation of frostbite and keep the brain alive at near zero metabolism. But let's be clear, when you are truly frozen, you are not sleeping. You are dead, clinically and chemically inert. What matters is whether you can be revived. To do that, you need a suite of technologies that sound like science fiction, but are steadily emerging in the real world. Nanobots or molecular machines to repair membranes as they thaw, AI-guided cellular reconstruction to restore molecular structure, synthetic scaffolds that keep organs intact while warming, and perhaps a digital snapshot of the brain's neural state to verify that nothing essential was lost in the process. The results wouldn't be resurrection by magic, but a kind of precise reassembly, brick by brick, atom by atom, the same process our cells already perform, only faster and smarter. And that is a reminder that our cells already repair and replace themselves, so these same sorts of technologies can probably work even better on a living and mostly healthy subject to prevent aging. But even if you can age minimally or not at all on century-long voyages, you might still prefer to be frozen to skip a potentially tedious trip. There's also the possibility that future stasis does not involve cold at all. Some scientists have speculated about biochemical pauses achieved through nanotechnology or quantum entanglement effects, locking molecular bonds in stable configuration without temperature change. In essence, it would be freezing time rather than freezing matter, a different kind of cryonics altogether. This is not a near-term thing, but given the timelines for galactic settlement, if it is possible to do, we will probably have figured it out long before 99.99% of available systems in the galaxy have even received a flyby probe, let alone an Ark ship or Freezer ship full of supplemental colonists. And the value of cooling probes down to endure time is major too. Still, biological freezing remains the most straightforward route we can currently see for any interstellar settlement scenario that does not involve massive energy abundance on our part. I think we will get that, but even then, cryo offers a pathway to travel across centuries without the need for faster light engines or endless life extension therapies. A sleeper bound for Alpha Centauri does not need to be immortal, they just need to wait well. The physics and engineering of the Cryogenic Ark. A cryogenic ark isn't just a freezer with engines, it's a piece of thermodynamic art. Every piece of equipment in that ship needs to be able to work at subarctic temperatures. To keep people frozen for centuries, you have to wage a war against entropy itself. Every leak of heat, every flicker of current, every trace of cosmic radiation is your enemy. And the only thing you can never run out of is time. The first design priority is simple: temperature stability. You cannot afford a single power failure, but you also can't afford continuous high-power draw. The ideal cryogenic ark runs cold and dark, drawing just enough energy to maintain sensors, comms, and an occasional correction burn. The rest of the time it drifts into silence. Even the waste heat from those few running systems must be vented carefully behind, because too much warmth would stop thaw cycles in the cryopods or attract unwanted attention from telescopes light years away. You might even detach the rocket nozzles on your ship, letting them drift behind you in a long tether to cool, or even drift to the side to leave a false signal for anyone looking for you. And yes, you might be trying to ship colonists, or troops, or both, very quietly. Generally speaking, we should expand as a loose sphere out from Earth, and it'll be a long time for a newly settled planet wants or has the ability to send out its own colonists. As a result, newly settled frontier worlds will likely be drawing colonial expeditions from worlds closer to the settled core, not the fringe, and some of them might object strongly to gaining new neighbors. A cryo ship passing through the Oort cloud of some loosely developed star system en route to an empty neighbor draws a lot less attention than one running hot, let alone running its actual drive, which will generally be naked eye visible millions of miles away. Nonetheless, a cryo ship is a potential target of sabotage, being rather vulnerable, there's all the more reason to run as cold and dark as you can. This makes radiative efficiency critical. Deep space offers a near-perfect sink for heat, but not a perfect vacuum. Interstellar dust, micrometeoroids, and cosmic rays batter the ship endlessly at relativistic speed, and all of that is getting absorbed as heat, not just as damage and erosion. To endure this, engineers might bury the cryopods deep inside the ship, shielded by layers of bulk cargo, fuel, and metal foam. Ironically, the safest place on a starship might be its frozen heart, surrounded by shielding so thick the crew would never see the stars they are sailing between. The next problem is maintenance. A living crew can spot corrosion or replace a circuit board. A frozen one cannot. For that reason, a cryogenic ark would likely include a tiered automation system, small repair drones and diagnostics running continuously, and a larger supervisory intelligence that sleeps most of the time, waking only for scheduled maintenance or emergencies. This layer design minimizes risk. You're not trusting a single AI to stay sane and independent for centuries. We also don't rely on any single human technician who cannot be revived mid-journey or might go axe crazy. And to be honest, I think I'd trust a purpose-built maintenance AI over a person, or anything else with a personality that does not require it. Though as a reminder, while computation in general benefits tremendously from the cold, machinery doesn't handle ultra-cold much better than humans do. Things get brittle and crack unless built with such temperatures in mind, and may not operate at normal temperatures as a result. You may need entirely different drones and computer systems, each designed to operate when warm or cold. Purpose-built or not, no automation lasts forever. Radiation slowly flips bits in computer memory, polymers grow brittle and lubricants crystallize. To counter that, the Ark might carry multiple redundant brains, literal backup minds, sealed in magnetic vaults and woken only if the main intelligence degrades, and for cross-comparison for error accumulation. We would also see distributed architectures, with drones that periodically exchange code fragments to cross-check one another, like a ship constantly auditing its own sanity. That level of redundancy doesn't just protect the machines, it protects the people, because waking a frozen crew is risky. You only do it if absolutely necessary. A micrometeor strike, reactor anomaly, or a navigational correction the AI can't handle. I do wonder if nanometer might be more appropriate than micrometer when discussing interstellar travel collision possibilities. Regardless, ideally those revivals happen rarely. Each thaw carries medical risk, even if your cryonics process is flawless, and if you keep a small caretaker crew conscious to oversee the AI and each other, then each unexpected revival disturbs the social equilibrium of a mission designed to skip across the ages. You could imagine it as a kind of crypt in motion, its crew entombed below decks, while robotic caretakers patrol the corridors, keeping vigil over the sleepers. For centuries, it would coast silently through the void, its computers dreaming of starfields and status reports. Occasionally, a maintenance drone might stir, adjust a heat pipe, or polish a sensor lens. Otherwise, nothing would happen at all. And that's the point. In space, the less you do, the longer you last. If that sounds eerie, it's meant to. A cryogenic ark isn't a bustling generation ship or a gleaming exploration cruiser, it's closer to a mass tomb. It represents a trade-off between vitality and endurance, between the fire of civilization and the patience of the grave. But in that frozen stillness there is also safety. No mutinies, no diseases, no aging or boredom, no slow decay of morale or space madness. No second thoughts about going to live on an alien world. Of course, that raises deeper questions. What happens when the passengers wake? Will they still be the same people who departed? And their minds are preserved, but the world they knew was gone. Can you really say they survived the voyage at all? That brings us to the next challenge. Not the physics of freezing bodies, but the psychology of freezing identities. The problem of time and identity. The greatest challenge of cryogenic travel may not be technical at all. It may be philosophical. What does it mean to wake up centuries after you left? Unchanged in body, but alien in mind and circumstance. You might step from your cryopod to find your homeworld has forgotten you, your mission has been cancelled, or humanity itself has evolved beyond recognition. You could wake up millions of years from now in an alien lab, having drifted into alien space, or simply have been picked up by a civilization that originated from Earth, but so distantly they might as well be alien. To you, only days have passed. To everyone else, you're an echo from a vanished age, a ghost. Science fiction has often explored this paradox, the man out of time, frozen or relativistically displaced. Buck Rogers is the classic, Fry from Futurama, or Lister from Red Dwarf the most humorous, and I'd strongly recommend those for watching or reading Joe Haldeman's Forever War or Alastair Reynolds' novels House of Suns or Pushing Ice. or his Revelation Space series, including Chasm City. Alistair Reynolds writes a lot on this topic. It is easy to focus on the wonder, stepping from the Ark to see twin suns, alien continents, and new civilizations, but what we rarely ask is how the sleeper feels about it. For them, the voyage is instant, but its cost is everything they once were. Cryonic sleep is one-way time travel, and time travel is never free. I think that's a missed opportunity in the Alien franchise, an otherwise excellent sci-fi horror series. They use stasis a lot in the films, but rarely discuss the impact that would have on the crew. We get a bit of that at the beginning of the second Aliens film. There is a quiet horror in realizing the world you knew continued without you. Your family is dust, your culture extinct, your favorite songs now ancient curiosities. Some might see that as tragedy, others as liberation, a way to leapfrog history and begin again somewhere new. For colonists, it could be exhilarating, leaving a crowded Earth, awakening a frontier paradise, and starting over. For others, it might feel like being buried alive, only to rise in someone else's dream. That psychological strain is one reason why some visions of sleeper ships include crew families or frozen societies, groups who all awaken together, preserving some shared culture and language. Their frozen centuries become a collective experience rather than a lonely exile. You might even see the rise of chronocultural identities, people who define themselves not by geography but by an era, the 23rd century born, the second expansion sleepers. Then there's the issue of motivation. Who volunteers for a journey that skips entire epochs? For colonists, it's a chance to see new worlds. For others, it might be escape, from guilt, from punishment, or from an overcrowded civilization. Some writers have imagined prison ships, where convicts are frozen and awoken in distant centuries as their sentence. It's poetic, but not exactly just. Time is a poor instrument for rehabilitation. You wake the same person you froze, only displaced. And as punishments go, some might consider it a gift. They go to sleep after their trial and awake when nobody knows who they are and what they did. Even for volunteers, the ethics grow messy. If revival is not guaranteed, is cryogenic sleep just a sanitized form of euthanasia? If a crew is frozen for a mission, and centuries later someone else decides not to wake them, are they legally dead or still owed their place in society? Is it murder to smash open a cryopod with an axe? Cryogenic travel collapses the distinction between asleep, dead, and alive but not yet. A civilization that uses it widely might develop new laws, new religions, and new definitions of personhood. There's also the subtle question of identity through change. Suppose cryo does not perfectly preserve the mind. Some synapses shift, some molecules rearrange. If 99.9% of you wakes up intact, is that still you, or a reconstruction that merely believes it is you? We accept that biological continuity defines life. Every cell in our body is replaced over years, yet we remain ourselves. Cryogenic sleep might simply stretch that renewal across centuries instead of decades. You might need to keep digital copies of a mind to correct any damage during sleep, stored in a backup bunker on the ship or even on the world you left, where someone with extreme damage might need to either be shipped back to for treatment or to some world halfway in between with sufficient medical equipment, or just kept on ice till a copy can arrive and the colony can develop the infrastructure for the repair. You might have shipped out with your family and wake up centuries after settlement because you were damaged but they were fine. They may still be waiting for you, they may live a long time or go into cryo, or they might have moved on. Culturally, these ships would change humanity as much as they spread it. Imagine a society where the wealthy or curious can leap ahead in time by centuries, freezing themselves between the great events. Such time tourists might attend the next Renaissance, or wake only once every 1,000 years to check on civilization's progress. Their descendants might measure success not in lifespan but in epochs survived. And for the ships themselves, this temporal drift could shape entire subcultures. Some might make a profession of it, crews who awaken once every few hundred years to service their ship and then refreeze, slowly leapfrogging down the timeline. Others might live semi-cyclically, alternating between generations awake and centuries asleep, forming families and traditions that span millennia. In the long run, such sleep leaper cultures could become humanity's most ancient lineages, not because they live longer, but because they skip more efficiently through time. Which brings us to the question of how long these dreams can last before even perfect engineering and human patience fail. How long can we stay frozen before the universe itself thaws us out? Cryogenic arks force us to contemplate timelines that are massive on a historical scale, but even they are but eye blinks compared to geological and astronomical ages. Joe Scott's Nebula documentary, Oldest and Newest Place on Earth, reminds us of that as he travels from some of the oldest exposed rock on Earth to lava that's literally rewriting the map of Hawaii. Many of you already know Joe's work, so you know it's worth watching, and he and I have collaborated on a lot of projects over the years, including Nebula, the largest creator-owned streaming service, and where you can find tons of original, exciting, and educational content from us and many other awesome creators. It's also where every episode of SFIA premieres early and ad-free, along with a lot of bonus content like this month's exclusive, Chrono Engineering. To try it out for free for 3 days, use my link or the QR code on screen, and you get 50% off a yearly plan. Just $30 for the whole year, about $2.50 a month. Head to go.nebula.tv/IsaacArthur and start watching today. How long can we stay frozen? Freezing something stops chemistry, but does not stop physics. Even at absolute zero, atoms vibrate, decay, and transmute. Cosmic rays will strike, isotopes still emit radiation, and the slow erosion of time continues, indifferent to whether you're awake or not. So the real question isn't how cold you can get, it's how long before the universe itself unravels what you've preserved. Inside every human being are small amounts of radioactive isotopes, mostly potassium-40, carbon-14, and traces of polonium and uranium. They are harmless to a living person because our cells constantly repair the molecular damage they cause. But when you are frozen, that repair machinery is off. The same decay that once went unnoticed now accumulates, one atom at a time, in the DNA and membranes of every cell. Over years, that damage builds up. Over millennia, it can become lethal. In a normal environment, the internal radiation from your own isotopes is equivalent to only a few tens of millisieverts per year, trivial compared to everyday background exposure. But if you multiply that by thousands or even tens of thousands of years, those tiny hits add up to billions of DNA breaks and crosslinks that cannot heal until thawed. When revived, the result would resemble an organism suffering acute radiation poisoning, but from itself. Estimates suggest a cryogenically frozen human body would begin to suffer irreversible molecular decay after a few thousand years, unless protected by extreme measures. Cosmic rays would make matters worse. Even with meters of shielding, high-energy particles can still create secondary radiation cascades inside the hull. Travel at relativistic speeds does nothing to help this, blue-shifting every particle. Over geological spans, that trickle of energy becomes a sandblaster against perfection. Still, there are countermeasures. Before freezing, the crew could undergo a decontamination diet, living for years on isotope-depleted diets, grown in controlled environments using carbon purified of carbon-14 and potassium devoid of potassium-40. In truth, even a few months might help to remove most of the isotopes, and it is possible a more long-lived and radiation-sensitive future society might purify the nutrients in their regular food of isotopes. Doing this to people before a trip would not make them immortal, but it could stretch survival times by an order of magnitude. 1,000 years might become 10,000 before cumulative decay becomes a serious concern. And yes, while the technology to revive people is likely to allow radiation damage repair, at least to a point, we cannot send nanobots into a frozen person to repair them. They cannot swim through your frozen blood, and tiny machines are likely to be even more sensitive to cold than other devices. Another strategy then would be periodic repair cycles, thawing sleepers every few centuries for cellular regeneration. They might awaken briefly, perhaps for a year of rehabilitation and ship maintenance, before returning to hibernation. In that way, the mission itself becomes part of their therapy. Wake, work, repair, and return to dreams. Over millennia, that rhythm could let a crew survive indefinitely, skipping across time in steady pulses. This should permit even million-year voyages, sufficient to journey to a new galaxy, if not longer, seeking to outlast the galaxies themselves. A ship built to cross time, not space, simply parking in deep space orbit to wait out the cosmos. But there are still fundamental limits. Even in perfect shielding, random quantum tunneling events can flip atomic bonds over vast periods. Chemical bonds will gradually rearrange. Radiation from cosmic neutrinos will pass straight through any barrier. Given enough time, the the information pattern that defines a human body will degrade. On cosmological timescales, entropy always wins. Yet even if decay is inevitable, the principle of cryogenic travel remains sound for journeys of thousands or tens of thousands of years, if not much longer. For colonization on human or even historical timescales, that's more than enough. These sleepers might not be eternal, but they don't need to be. They only need to last until dawn breaks on another world. And, like all of humanity's most ambitious dreams, that's both a scientific problem and a moral one. How much time do we dare steal from ourselves? How far can we stretch the thread of identity before it snaps? And when we finally awaken, what kind of future will be waiting, or left, for us? For that, we need to look beyond the frozen vault itself and ask how we will use it. What kind of societies, ships, and missions would risk freezing entire populations for the sake of the stars? Crew dynamics and risk. Even in a ship where nearly everyone sleeps, there's still the question of who stays awake. A cryogenic ark may drift for centuries, but it cannot simply be abandoned to silence. Some system must steer it, maintain it, and defend it, and that means trust. A fully frozen crew leaves those duties to automation, but as we've discussed before, a ship run entirely by AI poses its own existential risk. True artificial intelligence, however reliable, changes over long periods of isolation. With no human correction or oversight, even a perfectly obedient program might evolve in unpredictable ways. You could minimize that risk by keeping it simple, dumb, maintenance bots with rigid parameters while the smarter portions of it sleep too, or by creating a hierarchy of machine intelligences that check and countercheck one another, like a miniature bureaucracy of tireless civil servants keeping vigil over their sleeping masters. Still, however good such a system is in reality, what matters is how comfortable people are with it. In an ultra-long-lived society, it might not be hard to find some introverts who felt like being awake for some or all of the journey. Any ship that allows for reanimation, periodic thaw cycles, or emergency wake-ups opens a new layer of complexity. Waking humans mid-voyage carries not only biological danger, but psychological strain. Imagine opening your eyes to find your ship adrift in unknown space, everyone you knew frozen, and a task list centuries out of date. For most, it would feel like being cast away in time itself. To make such a system sustainable, many designs propose rotating watch crews, perhaps 10 people awaken every century, performing inspections, data relays, and calibration before returning to sleep. Over a 1,000-year voyage, 1,000 people might serve a few waking years each. I would also stagger the wake-ups, not wake people in shifts. Maybe you got 10 people awake for 10 years at a time, and you wake one person and freeze one person every year. The current commander goes to sleep, and their XO has already been awake for 5 years when you wake up the replacement XO. It would create continuity, keeping the same generation alive across millennia, not through life extension but through time management. There's nothing stopping you from warming people repeatedly, but my guess is that everyone would only do one shift unless something required them to be awakened repeatedly, like the ship's current mechanic died in a maintenance accident, so you woke another one up who has already done a shift, or maybe the captain or colonial governor gets woken once a century for a year or two to review things. Maybe somebody misbehaves and needs to be put on ice and someone else awoken. Maybe just otherwise decent crew members just can't stand each other, and one goes on ice to work a later shift. In fiction, the more times you thaw, the more chances something goes wrong. This is probably exaggerated, but also probably true. Each freeze-thaw cycle carries risk: microscopic ice damage, protein misfolding, or cellular stress that accumulates over time. So the rotation is likely to be sparse. The social dimension cannot be ignored either. Suppose some frozen civilization regularly uses cryogenic travel. What safeguards prevent abuse? Could a government freeze dissidents under the guise of colonization? Could a cult smuggle its members aboard and secretly program their pods to awaken first, taking over the ship? Even well-intentioned sleepers could fracture into rival ideologies after a revival, each shaped by centuries of different data and shifting context, depending on what news was coming from home when they were awake or what the last shift passed on. One faction might decide to stay frozen forever, another establish a new colony, a third to return home. In the silence between stars, even the smallest disagreement could divide eternity. It's not hard to imagine cautionary tales, ships hijacked mid-flight, colonies that never arrive because their cryosystems fail, or sleeper mutinies where a tiny awakened crew seizes control before anyone else can protest. Such events would be rare, hopefully, but catastrophic, the stuff of history and legend. The risk isn't limited to human sabotage either. Micrometeoroid damage or nanometeoroid damage or cosmic radiation might corrupt the AI's mission parameters, sending the Ark off course or into an endless drift. Every safeguard must assume that sooner or later, something will go wrong. Beyond cryogenics, slowing time itself. Of course, freezing bodies is not the only way to wait out the centuries, even ignoring post-human minds that might be digitally uploaded onto computers and could simply pause their operations. Time itself can be manipulated, or at least experienced differently. Einstein's relativity tells us that time slows as speed increases, or as gravity deepens. If you could travel fast enough, or orbit close enough to a massive object, you could live a few years while the rest of the universe ages millennia. In a sense, that's the ultimate stasis, not stopping biology but bending time around it. A ship cruising at 99.99999% the speed of light would cross the galaxy in a few subjective decades, though hundreds of thousands of years would pass for everyone else. For the crew, the journey would feel swift. For the rest of humanity, they would be a myth. The cost, of course, is staggering. You would need near limitless energy, and shooting thick enough to withstand interstellar dust, striking with the force of atomic bombs. The cosmic microwave background itself would blue shift into deadly radiation storms. It's the cleanest theoretical route across the stars, and the most dangerous. Another hypothetical method is gravitational stasis, orbiting near the event horizon of a large black hole, or between two binary black holes, where time slows to a crawl relative to the outside universe. To external observers, the ship might seem nearly frozen. To those aboard, only moments would pass. It's technically the same principle as relativistic travel, but without the acceleration cost. The problem, of course, is the neighborhood around a black hole is hardly safe. Intense tidal forces, radiation, and extreme precision requirements make it a poor choice for peaceful slumber. But then we've contemplated building artificial worlds around black holes for their economic advantage, and they might maintain lower levels that were slow time zones. Slowing time through gravity is a lot harder than one might think, especially as any slow time stasis field needs to run uniformly lest your head age faster than your feet, or get ripped clean off. Still, the underlying concept, controlling time rather than metabolism, might one day be achieved through more exotic physics. Artificial gravity wells, warp metrics, or quantum time locks could offer true stasis, regions where internal processes simply halt, like a cosmic pause button. We might one day build stasis fields, where the passage of time can be slowed to 1 part in a trillion. For now, though, that remains squarely in the realm of Clark Tech, our name for technologies that look like magic because physics hasn't quite given us a map to reach them yet. Until then, cryogenics remains the most attainable bridge across centuries. It may never match the elegance of relativity or the wonder of time manipulation, but it offers something tangible, a cold, careful defiance of decay. With enough ingenuity, we can sleep through the slowest voyages, endure the dark ages between stars, and awaken when the universe has changed. The cryogenic ark then isn't just a machine, it's a promise that even when the fires of civilization cools, humanity's dreams can endure the long nights and wake again.